So if you go back and you find this equation here, so you take the 4x plus 2, you integrate it. So obviously you go up 1 to 4x squared, you divide by the 2, you go up 1 to 2x, you divide by the 1, you remember to add the c, and what you have here is the integral equation. So if you want something to call it, I often refer to it as the original equation, but obviously if they give you the gradient function, then it gets a bit confusing if we start calling things original things. So that's the integral equation. And obviously, if you have one point in your graph, you can now find the full equation because you can find c. Okay? So that's what we've done up till now. Now you're going to use it for its second main thing, and that's to find the area underneath the curve. It's important that you understand what dy and dx is. If you remember, these are gradient, right? You're looking at the way y changes or the way x changes. That's the whole point. It's the gradient function. You're ending up with a gradient. So dx is the way in which x changes, or the change in x, okay? Because now we're going to use dx by itself, so it's important that you understand what it means. So if you look at this example, okay, also definition of a definite integral. So we have two types of integrals. We have three. We have improper integrals, which we'll deal with later. They get their own lesson. And we have definite and indefinite integrals. This one is an indefinite integral, because we can't see where it's starting and ending. It's just an arbitrary little sign. And by the way, that S means sum of. Okay, so that means sum of. And you've been using it just as a symbol, but you know what it means. It means integrate. But when you integrate, you're finding the sum of something. Okay, that one's indefinite. This is a definite integral. So again, this is just terminology. This one is saying you're going to integrate the area between x is 0 and x is 3, right? So that's a definite integral. Now, to explain to you what is going on here, I'm just going to, come on, respond. Okay. Move this up. So this is a little velocity time graph. And because it's a rectangular function, it's very, very easy to understand. So I figured the best way to explain this to you was to show you something in real life that you should understand fairly easily. The difficulty is because we're talking about velocity in terms of time, instead of y in terms of x, there's a slight, that might be very, very slightly confusing to you because I'm using different symbols from usual, but hopefully not too much. So this is showing something that is going at a constant velocity of 10 meters per second, so that you can see that after 1 second, you've obviously gone 10 meters, and after 2 seconds, you've obviously gone 20 meters, and so on. It's very easy to see, right? So the area underneath that graph is, in fact, the displacement, which is what the original function was that you would have differentiated to get the velocity function, right? So if you look at it, the velocity function over here is 10. It's y is equal to 10. That's the line that we have going across here. So if I ask you what is the equation of this line, that's the line y is equal to 10. That's the velocity function, right? That's the gradient function. So if we integrate it, okay, then we're going to go up 1, and we're going to add c. So you agree that the integral of 10 is 10x plus c, no problem, right? Yeah. So that is our integral equation. That is one stage further up. And you should know that if velocity is your gradient function, then your original function is displacement, right? So this is a function for displacement, which, as it says over there, so it's the displacement function. And you know that you did this when we were doing this in year 11. So you would have those graphs that came up like this, and they would say to you, and it would be a speed versus time graph, and they would say to you, what is the distance that the person traveled? And you would go for the area underneath the graph, right? And you'd add the blocks, the rectangles and the triangles, and you'd know the area under the graph. And so you already know that the area under the graph is the displacement. You already know that the area under the graph is the previous function. Okay. So I'm saying that this is, if I integrate that, I'm going to get 10x plus c. Now this is how we write it. If I want to know the distance that has gone between 0 and 9, right? Then I write it with a square bracket round here. This is after I've integrated it, okay? So the very first step over here, this is before you've integrated it over there. Then you integrate it and you change it and you write it in that bracket like that. And you must get used to doing it so you have to do it properly, right? And basically, this started at 0, ended at 9. If you go back to the original graph, you can see how far you go by how far is underneath there, right? If you're going to go 10 meters every single second, then after 9 seconds, surely you've gone 90 meters, surely, right? And you can see it over here. The area of this thing is going to be the height of the thing, which is 10, times the length of the thing, which is 9, 10 times 9, and that's 10 meters per second times 9 seconds. And notice how everything cancels out nicely. You've got meters per second, the seconds cancel, and you can see that it's gone 90 meters. So you can see clearly that the area underneath the graph is the displacement. In this case, if we're talking about displacement, we're saying that that car or whatever has traveled 90 meters. We're not saying 90 meters squared. Please don't get confused. The area underneath it, in this case, is displacement because this is a speed time graph. It will depend on what the original graph is, what the area actually means. But it is definitely the area. So you could also refer to that as 90 units squared, because it definitely is. Okay, not 90 meters squared for obvious reasons, but it is 90 units squared. If you go and you use the integral, so this is now called the integral function once you have already integrated it, and you've got 10x plus c, then what you do to work out the distance is you take the big value and you plug it into the formula that you've got. And then you take the little value, and again you plug it into the formula that you've got. What you're doing is you are subtracting the area from 9, or at least the area from 0, from the area from 9. So let me just show you what I mean. Carry on. So you don't need to put c in because c will end up subtracting c, but you can see it works. There's the 90 meters, right? So that's what we're going to do, but we're going to be doing it with much, much fancier things than that. So to give you an idea of what's going on in terms of this method, do I need to, let me just... So this is now a velocity time graph again. And this time they have given you velocity is equal to t, 8 minus t. And obviously, straight away, you could make this into 8t minus t squared, which is going to be infinitely easier to integrate, which is what we're going to want to do with it, right? And what you're basically doing is you're going to work out the area underneath it, and if you work out the area underneath it, then you will have displacement. Or you'll have area, depending on which one they ask you for, right? So what you're going to do is you are going to integrate the velocity function, right? So that's the gradient function. And you can see I've got the velocity function there. I'm going to integrate in terms of the same variable. It has to be dt if the thing's got t in it, right? And now it's in the right format, ready to integrate. And that will give me the area up to any point underneath there, okay? So if I want the area up to t, then I'm going to just use that piece and I'll put in t. And notice how it starts at 0 and ends at t if I want the area up to t, right? What you're doing is you're taking the area underneath that graph and you're breaking it into tiny rectangles. So you can see that if you estimated the area of that thing using the picture directly above it, if you know the width of each one of those bars and you know the height of each bar, then you can work out the area of the bar. Do you agree? And obviously it's not dead accurate because the graph doesn't fit it perfectly, but you'd get a reasonable estimate, okay? And that's what we're doing. The difference is we're going to make those bars so tiny, so we're going to make dt tend to 0. You understand? Remember what dx is. Dx is the change in x. So if we make those bars super narrow, then it's going to fit a huge amount better, okay? So next, there we go. Okay, so we are trying to work out the area underneath that curve. And you can see I've shaded one of those blocks there. And you can see that the formula to work out the area of the block is going to be obviously the length of the block times the width of the block. Note what the width of the block is. I'm actually just going to make this a bit bigger. The width of the block is the change in x. It's either dx or in this case dt because this is a graph about time, right? So that's obviously the width of the block. The height of the block is the y value. It is the formula, right? So over here we've got vt is equal to 8 is equal to t minus at least times by 8 minus t That is your y value, right? If you go here and you look at the top of this block and you're looking at the height of the block, that's your y value. And your y value happens to be equal to t minus 8 minus t. It is the velocity formula, right? That's the y value, that's y. Why is that, right? So you're looking at y value times by the difference in the x value, right? And obviously, if you add up all of those little blocks, and you do that, then you're going to more or less have the area underneath the curve. So if you look at the area of the region over here, it says the area of the region is the sum of, I'm sorry, my sum symbol is rather terrible, and then it's Vt, which is the height of the block, right, times by dt, which is the change in x, the little width of the block, right? And obviously, it would work much better if we broke it up into blocks like that one over there, right? If we break it into teeny, teeny, tiny little rectangles, then we're going to get a much better estimate of the area underneath the thing. And that's what we're doing. So just like when we were doing the differentiation from first principles, and you made h tend towards 0, so that the 2 points became the same point, you're now making dx tend towards 0, so that those blocks become infinitely thin, right? If they're infinitely thin, then that thing is going to fit perfectly. Okay. And so this is where the formula comes from. So hopefully it makes complete sense. So basically the area of the region is going to be the sum of all of these things added together. And we are going to have the y value times by the x value for all of those little blocks that we're going to add up, right? And at the same time, the change in x, dx, is going to tend towards 0. So those blocks are super, super thin. This is the same thing as this. This is exactly the same thing as saying sum of, right? The y value of Vt, which is 8 t minus t squared in terms of time. That's exactly what this thing is saying. That's where it comes from, right? It's literally saying you're going to work out the areas of all those teeny tiny blocks, add them all up, and you will have the area, obviously. That's what it's saying, right? So that's why integrating gives you that. You can also see you can also see it from here. The area of the block is going to be the y value times by the change in the t value times by the dx value, right? And so you can divide both sides by dt, and we can see that the area over dt is equal to vt, but we know that vt is equal to ds over dt because that's how we got it. We differentiated ds. And we know that area divided by dt is also equal to vt. So clearly area is ds. They are the same thing, right? So if you look at their positions in the equations, they are clearly the same thing. You can also see it from this one over here. If area is equal to vt, which is dy over dx, remember that's what you've done. You've looked at the change in the y with the change in x, and then you're timesing it by dx, then area is equal to dy. That's your original formula, isn't it? Right? So that again proves to you that the original formula, the integral function, is dy, and so this is all working, right? So hopefully it's very, very clear. So if you have a situation like this, so if you go back and you work out the integral function for this velocity function, obviously it's a cubic, no big surprise. If you take any point on that cubic, any time on that cubic, and feed it into the cubic function, you will automatically get the displacement at that time, right? But we can also get the displacement at that time by using the velocity function, and all we do is we decide where we're starting and where we're ending, and we can work out exactly how much displacement is there. You could do it here. You could take these values, plug them in here, work out the displacement there, work out the displacement there, and subtract, and you could find it as well, right? But we're going to be working from the gradient function, not from the original function. So over here, this is your formula for displacement. This is your formula for velocity. The formula for velocity is dy over dt in this case. And your area is going to be the integral of that one, because that's the height, times by the change in x, and you're adding up all those little blocks, right? Stop. So again, if you have a look at this, this is basically what you're doing. So this is the basic formula for what you're doing. Let's just make it bigger. You're saying that you're going to take the gradient function, you're going to differentiate it, and you're going to end up with the integral function. Then you are going to substitute in both pieces of the integral function, that's a and b, into both of them into the same formula, right? So you'll have the formula with maybe 6 and 6 in it, minus the formula with 2 and 2 in it, right? So the whole formula twice, because you're going to take the area up to the end of A, and then subtract, or at least the area up to the end of B, and subtract the area up to the end of A, so that you can get there. Don't worry, it's not hard. You'll see in a minute. So that gives you the area underneath the parabola, which is the distance traveled between 8 and 10 seconds. And here's an example of what you would do. Now, this is with 0 to 8, but you can put any values inside there. And obviously with 0, everything becomes 0 and it disappears, the second one. But if it's 1, if you're going from 7 to 1, the second one is not going to disappear anywhere. Okay? So they're saying to find out the area underneath the graph between 0 to 8 seconds, or alternatively find the displacement between 0 and 8 seconds, because they are the same thing, right? So the first thing you are going to do is you are going to find the integral function. So you're going to integrate it, okay? You don't need to use the c, so you can ignore the c. I've still got it there, but that's just to show you again that it disappears. So you don't need to write it at all. Don't write it. It's a complete waste of your time. Then you write down the limits that we're going to use. This is a definite integral, so we know which area we're looking for. We know where we're starting. We know where we're finishing. You write them with a square bracket like that. The only exception is sometimes they don't bother with this bracket on that side. So if you feel like just writing the 1, you can do that. I'd prefer you wrote with both. Then what you do is you get it into its simplest form, and now you substitute this one in. Then you substitute that one in separately into separate equations, and you subtract them from each other. So you substitute the 8 in there. Wherever the t is, you're sticking an 8. And so there's another t, you stick another 8. So there's no mixture. You don't have a mixture between 8 and 0. It's all 8. And this one is all 0, right? That's a 0. And then you work it out. So this one adds up to 85.3, right? And that's rounded off to 3 significant places. This one adds up to 0 because, you've got 2 times 0 squared, etc. And then the minus c and the plus c, they cancel out. So again, you can see that c doesn't matter, so you won't bother to mention it at all. There's just no point. And this is the area under that curve between 0 to 8 seconds, which up till now you've not been able to calculate. And this is now an example showing you, again, the original one that we did. Same thing. You can see from the diagram that the area under the curve between 2 and 7 seconds, you can see that it's 50 meters, right? Without any doubt. Height is 10, width is 1, or at least is, height is 10, width is 1. You've got 5 widths. It's going to be 50, you agree? And if you use the formula, so there you go, you make the integral formula, don't bother with a c. Starting at 7, ending at 2, substitute in the 7, substitute in the 2, and there it is, exactly as you'd expect it to be, right? So again, same thing at the bottom of the page, but starting with 1 and 7. So again, of course, I'm using the same formula. This time I haven't bothered to write c because it's a complete waste of time. Substitute in 7 there, substitute in 7 there, substitute in 1 there, substitute in 1 there. You make sure to not make silly mistakes and use this minus sign for the entire second bracket. Otherwise, things are going to go very wrong indeed, right? And that will give you 78 meters. That's rounded off. I don't know why I didn't put the 0 in. That's rounded off to 3 significant figures, right? If you do something like this, exactly the same, all you do is you work out the integral function and you subtract them from each other as usual, right? If you have this example here, so this is the last little bit of theory. If you go and you work out those 3 areas separately and you add them together, the middle area is going to give you something negative. If you add the negative one, then you won't get the overall, say this is the car is reversing. So where the car is reversing, your displacement is negative, right? If you go and say that that doesn't count, so you've gone forward 6 kilometers in total, and you've gone backwards 1 kilometer, and now you say you've only gone 5 kilometers, it's how much you've moved. It's in total, which is 7 kilometers, not 5. Okay? So you are going to do the absolute value of the negative one. In other words, you're going to make it positive. That's all you have to do. So if you end up with one below the line here, if it's below the line, it's going to give you a negative value. Please remember, if they're asking you for area, there's no such thing as a negative area. So if you get negative 40 units squared, you write equals 40 units squared. And for these ones, if you get negative 30, you ignore it. You make it into, well, you put the absolute value sign around it. And this is 60 plus 30 plus 50 in my made-up example. And that's going to be 140 units squared. That's it. There's nothing more complicated than that.